For this video, we are going to solve for the image and pre-image of the given vectors here, but using this linear transformation defined by a matrix. But of course, we need to start analyzing the type of vectors that are part of the domain and the codomain, so that we would know the correct processes, because it doesn't necessarily mean that it is vector v, this is already part of the domain and we're solving for its image, and the w is solving for its pre-image. Our matrix here is a 3 by 2 matrix. In short, it is by m by n matrix, where m is 3 and n is 2. We already have this understanding if we talk about linear transformation defined by a matrix. The linear transformation is actually computed as r to the n mapped to r to the m. That's m. Okay. In short, our linear transformation here could be r. Our n is 2, and we have to r3. In short, this is really correct now to be part of a domain, and this is the vector we're solving for an image, which is an r3 image. This is also already an R3, therefore we're solving for its R2 pre-image. Okay, so you really need to understand this first before jumping into conclusions. Now let's start to solve for the image of vector v. We're going to use this definition for a linear transformation defined by a matrix. The transformation of vector v is actually the product of your matrix A and the said vector v. Another thing aside from this that you would know that your operation is correct is once you plot this matrix A, you have 4, 0, 0, 5, 1, and 1, and multiplying this to your identified vector v with two components, you would see here a product that is defined. Okay, because if you're going to push for w here, meaning there are three components, the product will not be defined anymore. This could only be defined using two components of a vector, because you're going to multiply it like that as well, and as well like that. That's your hint as well. So this is really correct, that our v would be on r2 and this is r3 we're solving for. So we're going to solve it by simply multiplying. 4 times 2, that's 8. 0 times 2 is 0, so you have here 8. 0 times 2 is 0. 5 times 2, we have here 10. 1 times 1 rather is 2. 1 times 2 is also 2. So we have here 4. This is the image of vector v. In vector form, this is 8, 10, and 4. So we're done with the first half. The second half, we'll now talk about the solving of the pre-image of vector w. So the pre-image should be an element of our domain. So R2, we're expecting a vector that is element of R2. Same thing, we're going to use the same process here. Is equal to A times the vector v. But this will be equivalent to your w, because this is already given from this. This is what we're looking for. And again, since the vector v is part of the domain, our v here also has two components. So we have v sub 1 and v sub 2. So multiplying that, you will have 4, 0, 0, 5, 1, and 1 to be multiplied by vector v with components v sub 1 and v sub 2. And it is equal to your w, which is 4, negative 5, and 0. Hence here, we will have equations. Okay? We will have the first equation, 4 times v1. So we have 4 v sub 1 and 0 v sub 2. This is equal to 4. The second equation, 0 times v sub 1 and 0 v sub 1. You have 5 times v sub 2 is equal to negative 5. And the last is v sub 1 plus v sub 2 is equal to 0. Of course, with this, v sub 1 is already 1. Okay? For this, we have v sub 2 is dividing both sides by 5, you will have negative 1. You're already done with v sub 1 and v sub 2, which comprises the pre-image of your w. But of course, you can use this as checking. V sub 1 is 1 plus negative 1 That's 0, 0. This means that these really are your components. In short, the preimage of vector W is of certain vector V in R2 with components 1 and negative 1. So this is how we solve the image and preimage of a linear transformation defined by a matrix. Thank you very much for watching.